So the molecular formula tells you the actual number of atoms in the molecule. Now, you may or may not remember the empirical formula. Anyone remember the empirical formula? Little bit? Okay. If you do, that's great. The empirical formula for C2H6 is CH3. Okay. And we're just going to take a look at a bunch of other ones here. And you can see if you remember it, and if you don't remember it, see if you can spot the pattern. Okay, this worksheet is actually for my regular Chem 11, and they haven't seen empirical and molecular before. So we have methane. Remember, meth means one carbon. Prop means three carbons. Okay, and we had ethane up here. Eth means two carbons. And then but means 4 carbons. All right, so we have molecular formula, CH4, empirical formula, CH4. C3H8, C3H8. Oh, those are the same. Butane, C4H10, its empirical formula is C2H5. H2O2 becomes empirical formula HO. Dinitrogen tetroxide, the molecular formula, N2O4. You can see there's 2 N's and 4 O's in the molecule. The empirical formula, NO2. And then we have butene. And just so you know, that ene ending tells you that we have an alkene, which I don't think we've talked about before. Okay, and if we go up here, if you remember, the ane is for an alkane, and alkanes have all single bonds. Single bonds. Okay, so an alkane is made of carbon plus hydrogen with all single bonds. So we have methane, propane, butane, all made of carbon and hydrogen, all with all single bonds. Butene is an alkene, and what's different in our alkene? There is a double bond. So alkenes are carbon plus hydrogen, and there's going to be one or more double bond. You will never be tested on this organic chemistry stuff. It's not part of AP, okay? It's kind of a little bit part of Chem 11, but we have so much to get through, I'm not going to test you on it. But when you go to university, if you're planning on taking chemistry, having this little bit of background will help you out, okay? So tell your partner what the relationship is between the molecular formula, which I'm going to call MF, and the empirical formula, EF. What is the relationship between those two? How do you get from the molecular formula to the empirical formula? Okay, so what do we have to do to get from our molecular formula to our empirical formula? We have to simplify it, just like a fraction. Okay, so our empirical formula, we have to, simplify. So if you can't simplify it, the molecular formula and empirical formula will be the same. If they have a common factor, they will be different. And the molecular formula will always be some multiple of the empirical formula. Yes? So the molecular formula, I'm going to start calling it MF because it's really irritating to write that all out, is always a multiple, even if that multiple is 1, right? It can just be 1 times one times, 2 times, etc. of the EF, the empirical formula. Okay, and what I'm going to get you to do is just quickly do these exercises to see if it makes sense for you. Just make sure you've got that in your head. We'll spend about 5 minutes doing that maybe. I am recording. Yes. Yes, no problem. All right, so if you've finished, you can check your answers up here. And when I say check your answers, you can see if I've made any mistakes, because this morning I managed to simplify 2 of them incorrectly, which was pretty sad considering the math is so simple. Have I made mistakes this time? Have I done okay? All right, good. I learned my lesson this morning. Good. Now, notice while we're here, we have that "ene" ending. Yeah? And what do we see here?
Double bond.
Double bond. We again have an "ene" ending and a double bond. Carbon dioxide is just carbon dioxide. Benzene is its own funky little thing, and if you do take organic chemistry, you will see a lot of it, but we won't spend much time on it. And then if you see cyclo in front of a compound, it means it forms a ring structure. Okay, so it's going to be either like, if it's 3, it'll form a triangle. If it's 4, it'll form a square. If it's 5, it'll form a pentagon. If it's 6, it'll form a hexagon. Okay, if you see cyclo, it means it's a ring. Like I said, benzene is its own thing, so that's why it doesn't have cyclo in the front. All right, and you'll notice, are there any double bonds in cyclopropane? No, that's why it's propane. Yes? No double bonds. Okay, so if you had to define molecular formula and empirical formula, describe to your partner how you would define that. Edward, would you like a partner to talk to? You're good? Okay, just checking. So what is a molecular formula? And you can just kind of like throw words at me and I'll make them into a sentence. Double? Is it always double?
Isn't it like the original formula?
The original formula that tells you what?
The exact number of, like the amount of each element.
The amount of each atom, the amount of each element in the amount of atoms of each element in the compound. So it tells you the actual amount. Okay, so the molecular formula, and you're never going to have to define this, you just need to understand it. Okay, it tells you the actual number of atoms of each element in the compound. So it's quite informative, yes? The empirical formula.
Simplified version of the molecular formula.
Simplified version of the molecular formula. Addie, did you want to add something to that? It shows the ratio between the atoms. So I'm going to give you like a nice succinct way of saying it. Do you guys know the word succinct? It means short and to the point. Yes? It says what you need it to say without saying too much more. Yeah? So the empirical formula in succinct words is the simplest whole number ratio of elements in a compound. Is good? Okay. Another word that also means succinct is concise. I remember learning those two words when I was in grade 10 in my English class because our English teacher wanted us to be concise and succinct. So anyway, yeah, so that's basically what the empirical and molecular formula are. Molecular formula is we tend to use it for covalent compounds. Right? Because if I give you C3H6, that gives you a lot more information about the actual molecule than if I give you CH2, right? Because quite frankly, if I give you CH2, there's two other compounds that also have that same empirical formula. Now, there's a couple of them that have the same molecular formula as well, and then you would have to show the structural formula to get the full detail. But usually, we just go with our molecular formula. The empirical formula is very useful for what kind of compounds? Ionic, because do you ever know exactly how many ions are in a crystal? No, because the crystal could be big, the crystal could be small, it could be anything in between, it could be different now and tomorrow, and yeah, okay? Now, that does not mean that we do not use empirical formulas for covalent compounds. We do, because the word empirical actually means, and we can go to our next page, empirical literally means found by experimental means. So we might take a covalent compound and do an experiment and find the empirical formula, okay? And we are going to eventually, along the way, do our own experiment where we find the empirical formula. For today, we're going to work with numbers on paper. So what we can do is we can use data from experiments to find the ratio of moles. And guess what the empirical formula is? It is the simplest ratio. Yes? And we have here a little poem that helps us remember how to do this. Now, you can actually figure this out from first principles. If you know that empirical formula is the simplest ratio, like of the number, that would be the simplest ratio of moles. So in order to find the ratio of moles, you would have to find the moles. Yes? Can't find the ratio of moles if you don't have the moles, so you have to find the moles. And how do you find a ratio? A ratio, what mathematical process do you use to find a ratio? Do you add, subtract, multiply, or divide to find a ratio? You divide, okay? So now we've been like, okay, I need to find the moles and I need to divide to find the ratio. But here is a little poem to help you remember. And if anybody is musically inclined and would like to set this to music, it would make me extremely happy. I would learn it and I would sing it and we would put it on video so that you could like also learn it and sing it. And like you don't have to like do it in front of the class. You could just like teach me and I would do it in front of the class because I have no pride left. My singing voice is only, you know, but yeah, if someone wants to write a little song. At any rate, our little poem, we're going to put a big star beside it because this process of finding the empirical formula, people tend to forget it by the time they get to the AP exam because it is in May, not of next year, but of the year after that. So we're going to put a big star by this, and I'm going to make you say this poem a lot of times today, tomorrow, many, many times. So here's how it goes. Find the mass, mass to moles, divide by small, times till whole. Yeah? So find the mass to, divide by, times till. Okay, and now you're going to repeat after me. Find the mass, mass to moles, divide by small, times till whole. And now we're going to do it together. Find the mass, mass to moles, divide by small, times till whole. Again.
Find the mass, mass to moles, divide by small, times till whole.
One more time.
Find the mass, mass to moles, divide by small, times 1 whole.
There are so many less of you than in my block 2 class, and you guys did such a better job. And I'm going to post this on the video, and they're going to have to hear how much better you guys were at like participating. I'm like, oh, it does my heart good. So thank you guys. Give yourselves a little pat on the back. Okay. So what do we mean when we say find the mass? You need the mass of each element, because remember, we're finding the simplest ratio of atoms of each element. And how are we going to find the atoms of each element, or the moles of atoms of each element? We need our mass first, okay? Because mass is something we can find in an experiment. Find the mass of each element. So let's start with our first example and do step 1. Find the mass of each element. A sample of copper metal weighing 2.50 grams is heated to form an oxide of copper. Now, when they say an oxide of copper, all that means is that you have a compound that contains what? Copper and oxide. So it's going to be Cu something, O something. We don't know what our subscripts are yet. And then we are told that the final mass of the oxide, and when they say the oxide, that means the copper oxide. Yes, it doesn't just mean the oxygen by itself. This means our CuXOY is, oh, and I should do this in a different color. There we go. The final mass of the oxide is 3.13 grams. So we need to find the mass of each element. Do we know the mass of copper? Yes, it's given in the question. It is 2.50 grams. Are we given the mass of the oxygen? No, we're given the mass of the oxide, which is the compound containing copper and oxygen. The only reason it's got that name ide means it's an ion, and in order to be an ion, it's combined with its cation. Who's the cation? The cation is the copper, okay? So we know that the copper, this right here, is the mass of the copper oxide, and 2.50 grams is the mass of the copper. And if we subtract those, we get the mass of the oxygen. So find the mass. What comes next? Mass to moles. I like setting up my problem in this little chart. I'll explain why in a minute, but you don't have to use the chart. You can just show your work without all the lines and the whatsy-woos, okay? So we're doing each element. We found the mass of each element. Now we need to find the moles of each element, and you guys know how to find moles from mass, yes? What do you use to convert?
Moles.
From mass to moles, we use the molar mass. Okay, so we take our grams, and we have our grams on the bottom. Those cancel out, and we are left with moles. And we do the same for oxygen, and we find our moles of oxygen. Now, find the mass, mass to moles. What comes next? Divide by small. Now, in this case, they're almost exactly the same, yes? And quite frankly, they're going to be close enough to be exactly the same that you could probably stop at this point and just be like, my formula must just be, what's the ratio? 1-to-1, so it would just be CU 101, which is just CU O, okay? So probably you would not need to show all this work for this one. You could just kind of get to here and be like, oh, it's 1-to-1, CUO. But just for argument's sake, this is how I like to show dividing by the smallest, and I put it up here. Okay, you'll notice what I didn't do is I did not do this. Don't write this down. And the reason I didn't do that, anyone see it? This side of the equal sign is equal to 0.03938, yes? It is not equal to 0.03938 divided by 0.03937. So you cannot put something on the other side of an equal sign if all of a sudden it makes those two sides unequal, okay? It's just bad communication practice, yes? So if you want to show it like I show it, that's fine. I just do it up here and I'm like, I'm dividing, look at me dividing. And then I end up with 1 for each of them. Okay, so what I did is I divided and I ended up with 1 and I ended up with 1. Alternately, if you don't want to do that, you can use a separate line and you can be like, okay, I have copper, 0.03937 moles divided by 0.03937 moles is equal to 1. Okay, and then you can say oxygen, 0.03938 moles divided by 0.03937 moles is pretty darn close to 1. So you could show it that way, or you could show it up here. Doesn't really matter. And like I said, for a question this simple, you might just say, I know the ratio is 1-to-1. Done. Okay. So we divided by small. What's our last line of the poem? Times till whole. And we don't need to do it because these are both whole numbers. Yes? So if you get, and it's not going to be exactly 1, like, I don't know, it's like 0.999 something, right? But close enough. You're like close enough to 1. All right? Okay, here's another problem. We have a compound and it contains 16.7 grams of iridium and 10.3 grams of selenium. What is the empirical formula? So we know our mass, so find the mass. Oh, look, that's done. Mass to moles. Use our molar masses to convert. This time our moles are not the same, yes? So when we get to that third line, we're going to divide by the smallest. And who is the smallest out of those two numbers? 0.086. Okay, so we're going to divide by that one. And like I said, if you want to show that work on a different line, you could do that. You could say down here, I could be like iridium 0.08689 divided by 0.08689 is equal to 1. Or you can do it up here is equal to 1. And you could say selenium 0.1304 divided by 0.08689 is equal to 1.5. Or you can just have it up here and have your answer there. Okay? A couple things to point out here. You'll notice I got 4 digits here. I've found that 4 digits, if I write down 4 digits and I press clear and I lose my number, that's going to be enough to get me nice numbers over here. Okay, I won't end up with like weird rounding things where I have a number like 1.43 and I'm like, is that close enough to 1.5? Is it? I just don't know. But if you keep 4 digits, that's kind of a happy number. Do sig figs matter here? What are we finding? We're finding the empirical formula, which is the, yeah, and not just the ratio, it is the smallest whole number ratio. And if it's a whole number ratio, do sig figs matter? No. Okay, so don't worry about sig figs when you're finding empirical formula, but do keep enough digits that you end up with nice tidy numbers. Yes. Sorry? You know what? I just like to keep 4. I found I never have a problem with 4. Okay. I would go with 4. Okay. If you want to do 5, you can do 5. 3 sometimes will get you like things where you're like, oh, 1.44. Is that close enough to 1.5 to be 1.5? It becomes a judgment call at that point, and that's not nice. We don't want to make judgment calls. All right, so at this point, we would be like, oh, my formula would be, no, sorry, not IR. One, SE 1.5, but the last line of our poem says, times till whole. We don't have a whole number, so what do we need to multiply by here? We need to multiply by 2. Okay, so we take the whole thing, we multiply by 2. You can do it up here, or you can do it like this. Yeah, and then you would get IR2 SE3. Okay. This does mean that you need to know the decimal form of your very common fractions. A half, a third, a quarter. Yes? 2/3, 3/4. So what is the decimal form of 1/3? Decimal form of a third is? You guys don't know what a third is in decimal form? 0.333333. You can just say 0.33, okay? How about 2/3? 0.66666666, okay? Now, if you end up with something that ends in 0.3333, you will have to multiply by 3 to get a whole number because it's a multiple of a third. Yes? What if you have something that's 0.66666? You would have to multiply by, okay. If you have a half, obviously you have to multiply by 2 to get a whole number. Yes? If you have 1/3, how do you get rid of that third on the bottom? You multiply by 3. If you have 2/3, how do you get rid of that 3 on the bottom? You multiply by 3. Yeah? And then for quarters, you don't have to worry about 2/4 because that's the same as a half, right? So you should know 1/4 is 0.25 and you would multiply by 4 to get rid of that 4 on the bottom. 3/4, same thing, 0.75 you would want to multiply by 4. All right? And if you see something like my number, oh, my number isn't 0.75, it's 0.74. Close enough? Yes. Okay? If you get a number like 0.70, it probably means you've made a mistake because I'm going to try and give you numbers that are pretty good. Not always perfect, but pretty good. So 7.74 is pretty good. 0.70 is yucky. Yes? Yucky. There's always the outside possibility you might get a fifth, but it's very rare. What are your fifth fractions? What's 1/5? 0.2. What comes next? 0.4, 0.6, 0.8. All of those you would have to multiply by 5, okay? There are some exercises here. I would like you to try them. Okay, I'm going to give you a little bit of time to work on that. We're going to do at least page 110. If you finish that, you can go ahead and do a few more, and then we're going to do a demo lab. Yes? Yes. We just had a good question that might cause other people confusion, so I'll just mention it. And it's all about our diatomics. When we're finding the empirical formula that we want the ratio of atoms, right? We don't want a ratio of molecules. So when we are looking at O, we are looking at O atoms. And what we looked at over there was if you were to say, and don't write this down, okay, but like let's say we had 19.2 grams of, let's say we just wrote it as O, okay? That's going to be times 1 mole of O atoms for every 16 grams of O. Yes? You will get the same answer if you assume you have 19.2 grams of O2 times 1 mole of O2 per 32 grams. But then in order to find the O atoms, you would have to multiply by 2 O atoms for every 1 O2. Yes? And it will give you the same result either way, but this one is shorter. So it's easier just to work in atoms from the start. Okay, when you're finding empirical formula, just ignore molecules of O2, ignore your diatomics, because you're not looking for what it is in its elemental state, you're looking for what oxygen is in a compound. And if it doesn't make any sense to you, as long as you know you're finding atoms, it's okay to write this. It just takes a little bit longer, okay? We're going to look at finding the molecular formula, which is on page 113. In the moles book, 113. Now we're going to start abbreviating things because to write molecular formula is way too long for me. So I'm going to start calling the molecular formula the MF. And what do you think we're going to call the empirical formula? The EF. And it is true, hopefully you guys understand that it is true that the molecular formula is a whole number multiple of the molecular formula is a whole number multiple of the empirical formula. Yes, because the empirical formula is the simplified version. So the molecular formula will be some multiple of it. It might just be 1, but it might be 2, it could be 4, it could be 18, all right? So in order to find what multiple it actually is, you can take the molar mass of the molecular formula, which will presumably be given to you in the question, or it will be something that you can determine from other information in the question, or if you were actually doing a lab, you would find its molecular formula by doing some other experiments. Okay? And then if you know the empirical formula, which you have found by doing the calculations like you were just working on a few minutes ago, you can find its molar mass by just adding up the masses of the atoms from the periodic table. Yes? Okay. And when you do that division, you'll find a number n, and n is the multiple. Okay, so if the molar mass of the molecular formula and the empirical formula are the same, then n is going to equal 1. And so they will be the same. But if the molar mass of the molecular formula is twice the molar mass of the empirical formula, you'll need to take your empirical formula and multiply by 2. Okay? So that's basically all there is to this, and then we just put some fancy little bits and bobs in here. Okay, so we find the molar mass of the empirical formula by adding values from the periodic table. Whereas the molar mass of the molecular formula will be either given in the question or you'll be given enough data to solve for it in the question. Okay? So here is an example. If the empirical formula of a compound is H2O, and the molar mass of that compound is 18 grams per mole, what is the molecular formula? Now, when they say the molar mass of the compound, that means the molar mass of the molecular formula. And so that's 18. This is a trivial example. I hope you might even be able to see right now how trivial this example is, but it illustrates the point. So we then find the molar mass of the empirical formula, H2O. We have 2 hydrogens, which gives us 2. We have 1 oxygen, which gives us 16, and altogether that equals 18. So we take the molar mass of the molecular formula, divide it by the molar mass of the empirical formula. In this case, they are the same. And so the n, the multiple value, is 1. So we take our molecular formula and we multiply by 1. So the molecular formula and the empirical formula are both H2O. Yes? Okay. Here's a nicer one, more exciting. If the empirical formula is CH2O and its molar mass is 180 grams. Now, when they say the molar mass, that's the molecular formula. Okay, so that's going to be the molar mass of the actual compound, which is the molecular formula. So that's the molar mass of the molecular formula. So we can color code that one blue. Okay, so now we know the molar mass of the molecular formula. We need to know the molar mass of the empirical formula. Our empirical formula is CH2O. So we are going to find our C, our H2, and our O. That's 12 plus 2 plus 16 gives us 30.0. And now we're going to say, how much bigger is my actual compound than my empirical formula? You might even be able to do that in your head. It's 6 times. But, you know, let's assume you're showing your work on your AP exam. You would say, okay, I'm going to take the molar mass of my molecular formula and divide by the molar mass of my empirical formula. And I take 180, divide by 30, and I get 6. Now, if you do not get a whole number or something really close to a whole number, it means you've done something wrong. You've either calculated the molar mass of the empirical formula wrong, or if you had to find the empirical formula earlier, you might have gotten that empirical formula wrong. Okay, but you should get a whole number or something really close to a whole number. So if you're getting something more than like about 0.02 away, you should be like, you know, it'll be obvious. You'll be like, oh, you know, I've got maybe even like 4.97. You can be like, that's a 5. That's good, right? Yeah, you're close enough. But if you start getting like 0.05 away, you might be like, I mean, I'm going to make my numbers nice for you. When you actually do real things with real data, sometimes your numbers are not so beautiful, but when you get it on a piece of paper, I can make them fairly beautiful. I might not make them perfect, but I'll make them beautiful. Okay, so we got 6, so we need to take our empirical formula then and multiply by 6. Okay. Ooh, here's another one. If a compound has an empirical formula of C2H3O and 0.57 moles of the compound has a mass of 98 grams, what is the molecular formula? So presumably you can find the molar mass of the molecular or the empirical formula, yes? We have 2 times 12 plus 3.0 plus 16 equals, that's what, 17 plus 24 is 37 plus 4 is 41. 41.0. Is that what you get? 43. Dang, you're right. It's 43. I can't do math. Thank you. That's why I have you guys here. 43.0 grams per mole. So that is our empirical formula, color-coded yellow here for our purposes. How are we going to find the molar mass of the molecular formula? We are told that we have 0.75 moles, and that has a mass of 98.0 grams. Molar mass is equal to what? What's the unit of molar mass? Grams over moles. So how about if we put our grams over our moles? Look at that. Grams over moles. So let's take our grams, 98.0, and divide by our moles, which is 0.57. And fortunately for me, I've done the math here. So there is our molecular formula mass, 171.9 grams per mole. Which one goes on top? Empirical formula or molecular formula? Molecular goes on top. Molecular is always going to be bigger, okay? And if your molecular formula molar mass is smaller than your empirical formula mass, you've done something wrong, okay? It cannot be. It might be the same, but it can't be smaller than. So we put those numbers in, we put our molar mass of the molecular formula over the molar mass of the empirical formula, and we get 3.998. And if you end up with something that close, that will round to 4. So our N value is 4. So we take 4 and we multiply by our empirical formula. 4 times 2 is 8. 3 times 4 is 12. And 4 times 1 is 4. And we get our molecular formula. Is good? Okay. Oh, this one's mean. Oh, dear me. The density of a certain gaseous fluoride of phosphorus. So first of all, you have to say, what the heck is a gaseous fluoride of phosphorus? It's like a P and an F, okay? So you got P something, F something, okay? So you're just like, okay, I got P and F, that's great. Now I'm given the density, E, okay? It's gaseous and it is at STP. Isn't it fortunate that we've been doing some stuff with gases at STP? Yes, okay. Determine the molecular formula of this fluoride. The empirical formula is PF3. So here's our empirical formula. How do you find the molar mass of the empirical formula? Just from the periodic table. Molar mass from periodic table. And this is our empirical formula. So P is 31, F is 19, and we get, what do we get? 88, perfect, okay. Ooh, I see something that I did that's really bad. What did I do here that's really bad? There's something wrong in the red box.
Why here?
Hmm? Yes. Sig figs, I forgot my point. 0. Okay, all molar masses when we are using our periodic table should end in 1 decimal place. When you use the one that's actually for the AP exam, they'll all have 2 decimal places. Okay? But for now, and then if you go to university and they'll give you whatever periodic table they want to give you, and then you can just go with whatever they give you. Okay? Now, how do we find molar mass given density of a gas at STP? So our density, I'm just going to go up here. Density is grams per, and it's given in grams per liter. And we want to find the molar mass, which is in, what's the unit of molar mass? Grams per mole. And this, of course, is for a gas at STP. So how will we go from here to here? What will we have to use? 22.4 moles per liter, yes? Yes? Oh, so many people nodding at me. Nobody's screaming, Spence, what the hell are you doing? Anyone want to scream at me? Yeah, what?
It's 1 mole for 22.4 liters.
Yeah, it's 22.4 liters per mole or 1 mole per 22.4 liters. Yes, I have put the 22.4 liters with the wrong thing because the one goes with the mole. The one goes with the mole. Sorry. Had to bring it up again. 22.4 liters per 1 mole. Okay, and that's what we were practicing yesterday, yes? Okay, so let's just take a quick look at that because we're running out of time, so we don't have time to write it all out. But we can see here, my molar mass is grams per mole. And I'm starting out with the density. It's a fancy arrow. Grams per liter. I need my liters to be on the top to cancel the liters that are on the bottom. And I want to have moles on the bottom. So that's good. That's liters per mole. And I know the 22.4 goes with the liters and the 1 goes with the mole. And then I take 3.93, multiply by 22.4, and we get 88.032. You do not need to round because you're going to be calculating a whole number eventually. So just leave the digits there. Don't round off too much. Keep like 4 digits, 5 digits, just so you don't end up with weird stuff. This is our molar mass of our molecular formula. This is our molar mass of our empirical formula. Take the molecular formula, divide by the empirical formula. Look, 88 divided by 88 is 1, or at least really close to 1. So the molecular formula will be the same as the empirical formula, PF3. Okay? And your homework is going to be to finish off pages 110, 111, and 112. And page 115, 116.